Alright guys, welcome to week 4 FRQ help video. Let's begin here. So part A, I start by giving you guys this piecewise function here. It says that it consists of two line segments. That would be here, that's a straight line, and also right here, that would be a straight line. It also has two quarter circles. That would be this one here and this one here. And it says the portion of the piecewise function on the interval from -2 to 2 is a parabola. So from here to here is a parabola, and we're given the equation of that parabola right here. And that's the graph of G. Now, if we let f of x equal the integral of G with a lower limit of -2 and an upper limit of x, also we want to let the limit of g prime of x as x approaches 2 from the left. So in other words, the slope from the left of 2 is, here's 2. So the slope from the left is going to be not equal to the slope from the right. In other words, since the limit from the left and right of 2 does not have the same derivative, then we want to remember at this point that's going to be almost like a cusp. You can't really see it, and that's why I actually included that. You guys won't have this little piece of information on yours because something that awkward didn't pop up. But for mine, this is a cusp. However, reading further, the limit of the slope as x approaches 5, and since there's no direction there, it means both sides. So from this side and this side, the limit exists. The slope is 0. So we have a horizontal tangent line right there at 5. So no slope here because it's a cusp, but we do have a slope here and it's 0. So just some stuff to keep in mind as we're working through the problems. All right, so part 1 says we want to find these three things. Okay, we need to find f of -5, f prime of -5, and f double prime of -5. You do need to show your work for credit. Okay, so let's go ahead and begin. So f of 5, that would be equal to the integral from -2 to 5 of g of x. That means we're going from here all the way over to 5. Now we've got two different parts on this function that we need to concern ourselves with. We have the parabola section. Now that's not a normal geometry figure that we have a nice formula for, so we actually will need to integrate that using normal integration methods. But we do have a nice integration method for a quarter circle, right? So I'm going to go ahead and start by splitting up that integral from -2 to 2. From -2 to 2, the part of g of x is this crazy looking function right here. So I'm going to go ahead and take a moment and write that out. And then, remember, we're going from -2 to 5. So I've gone from -2 to 2 so far. So we need to pick up at 2 and finish off at 5. And that much of our circle there, that much of our graph is this quarter circle. And we have an equation for a quarter circle. The equation for a quarter circle is pi times the radius squared divided by 4. Okay? Now, the radius of this quarter circle is 3. Now, as for this piece over here, we're going to have to simplify that a little bit. Let's start by doing the exponent, x plus 1 to the second power. That would be, I'm going to show my work over here. If you do x plus 1 to the second power, you're going to get 2x squared plus, I'm sorry, that's not correct. It's x squared. So it's x squared plus 2x plus 1. Okay. Now that we're going to multiply that by 2, and that's going to give me 2x squared plus 4x plus 2. And then we're going to combine all these terms in with it. So I'm going to subtract the 3x squared. I'm going to subtract the negative 4x. And I'm going to add the 2. So what I'm left with then is a negative x squared. Those cancel, plus 4. Okay? So rewriting this crazy looking thing, and the reason I did that is because yours is kind of like that on your chart. You're going to have to simplify it. I'm going to rewrite this now in a much cleaner fashion. It's negative x squared plus 4 dx. Notice here I don't have the integral symbol anymore. That's because I've already done the math for that one. So there's that. Oh, we're not quite there yet. We got to finish. All right. So this piece here we can simplify. That's just going to be 9 pi over 4. That's the area of the quarter circle. Oh, by the way, I just realized something that I didn't correctly state before. This is actually going to be a negative. And that's because this area here is below the curve. We got to be careful with that. All right. Continuing onwards. This guy here, to do this, there's no geometry, like I said, for this. So we just have to integrate it like normal. So, you know, for this one, you're going to do the power rule. You're going to add 1 to the power and divide by that number. And for this one, you just put an x next to it, right? Then instead of the integral symbol, we put brackets and we put our limits here. Okay. And what the brackets mean with those numbers on the outside is that means we're going to write 2 sets that are being subtracted from each other. One where we plug in the 2. Oh, I forgot my x there. And one where we plug in the negative 2. And bring down the 9 pi over 4 for now. Right. So this first one here is going to simplify to negative 8 over 3 plus 8. Next one over here is going to simplify to a positive 8 over 3. Because this negative 2, when you cube it, you get negative 8. And there's also a negative on the outside there, which will give you a positive 8. And then minus 8. So we actually just get the same answer that we had before, just everything's opposite signs. Bring down the 9 pi over 4, of course. More room for myself here. Okay. So I'm going to go ahead and distribute the negative here. So we have negative 8 over 3 plus 8 minus 8 over 3 plus 8. And then I'm going to go ahead and bring that 9 pi over 4 up, just like we have been, just kind of tagging along. Finding our like terms here, that makes negative 16 over 3. Combining these like terms here, we get 16. And then combining, or bringing that up, again, we get this. Tons of places to make errors here. In fact, I wouldn't be surprised if I've already made one, but I hope I didn't. Even I kind of screw up on these. There's so many places to make along the way. So you got to be neat and double check your work as you go. You want to avoid those errors. Now at this point you can get a common denominator. I'm going to go ahead and just say let's stop there. I think the one that I gave you guys on yours should simplify nicely. Yours won't quite look quite as nasty as this one. But I mean, technically, we could go a little bit further. We can get all three of these fractions to have a common denominator and put them together. You know, I guess I'll just go ahead and do it just because, you know, why not? So what's the common denominator then for 3 and 4 and 1? Well, it would be 12, right? So I'd have to multiply this fraction by 4 on the top and bottom, which would give me this. This one's going to be a pretty hefty number, 12 on the bottom. And if I do 16 times 12, let me see what I get for that. I don't have that memorized. 192. And for the top one, this one, we multiply the top and bottom by 3 to get that common denominator. And what we can do is we can combine these two together here to get 128. Then we have minus 27 pi over 12. Like I said, though, since this is an FRQ, in all honesty, I probably would have had you guys just go ahead and get it to the point where simplify it as much as you can. But you know, it should turn out fairly decent. You guys, it won't. But yeah, I mean, in all honesty, on your actual FRQ test, I would encourage you guys to stop while you're ahead. So as soon as you guys get to the point where, you know, you've plugged in your upper limit and your lower limit and you have your subtraction sign in there, I would just stop. I wouldn't do any math. As soon as you got your upper limits and lower limits plugged in, just stop. There's no sense in doing all the work after that. You'd probably get a wrong answer. It's just too many places to make an error. Anyway, that's the hardest one for number 1. That's f of 5. The next one is asking us to find f prime of 5. So if f of x is equal to this, then f prime of x is going to be the derivative of this g function. Now, or this integral function here. And this is the second fundamental theorem of calculus. When you take the derivative of an integral, they just cancel out. And what you're going to be left with then is just g of x. So if they want us to find f prime of 5, then that means just find g of 5. In other words, what is the y value for the g function at x equals 5? What's the y value at that point? The answer is negative 3. The next one is asking us to find f double prime, right? Well, first of all, we know that f prime is this, right? So that means that f double prime is equal to g prime. So f double prime of 5 means we want g prime of 5. Now this is a graph of g over here. So g prime represents the slope then. So basically what this sentence here is saying is it's saying what is the slope of the g function at x equals 5? Right here at 5. Well, we said earlier g prime of x as x approaches 5 is 0. So the slope of the function at that point is 0. All right. Go ahead and move on to number 2. Oh, to see how you'd be graded on this, of course you'd have to show your work, but basically 1 point for every part. So that's a 3-point question. Now, they probably wouldn't ever really ask a question like, I've seen them ask questions where they ask for 2 of these. Usually it's these 2. I just threw this third one on, but technically it could be these 2. But I've never seen them do one where they ask for all 3. But when they do it, they usually count each one as a point. So I'm going to just say this one's worth 3 points. So for number 2, it says find the relative extrema of f. Okay. How do you find relative extrema of f? Well, first of all, you have to find the critical values. The critical values are where the derivative equals 0 or where the derivative does not exist or is undefined. Well, we've already determined that f prime of x is g of x, right? So we want to find where is g of x equals 0, or we want to find where g of x does not exist. where does g of x equal 0? Well, g of x equals 0 right here and here. In other words, wherever it touches the y-axis. Okay? Where is g of x? Well, let me write these down really quick. So we have two places where there is a relative extreme, -2 and, or, let me rephrase that. We don't have necessarily a relative extreme there. We have critical values. Next, we need to find where g of x doesn't exist. Well, g of x has no holes, gaps, or jumps anywhere. So this does not apply. I'll put DNA does not apply. Okay? Now, the next thing we have to do to determine what or if there are any relative extrema is we have to look at it. Now, a critical value is a relative min, I'll put R min, if f prime goes from negative to positive at that point. It's a relative max if f prime goes from positive to negative at that point, and it's nothing if there's no sign change. Okay, so let's take a look at x equals -2. Now, for x equals -2, does f prime go from negative to positive, positive to negative, or is there no change? Well, a better way of thinking about it would be as g, not as f prime, just for now. Does g go from negative to positive? Or does it go from positive to negative? Well, let's see. It goes from, g is positive here because it's above the y-axis. And to the right of that point, it's still positive. It's still above the y-axis. So it went from positive to positive, and therefore there was no change on the g graph, which means there was no change for f prime, which means that this is not a relative extrema. Let's check out x equals 2, though. At x equals 2, g, the function g, is going from a positive to a negative. So g is going from positive to negative, and g is f prime. That means f prime is going from positive to negative, which means it's a relative maximum. Okay, so our answer then to this question will be, that was me just teaching, but here's how you should write it. You should say x equals 2. Oh, let me back up a little bit here, because this how they word this question matters. If they said where is the relative extrema, then you would say x equals 2. But if they actually ask for the relative extrema, that's a y value. Okay, relative extrema are y values. So you'd say f of 2 is a relative max. So the relative max occurs at x equals 2, but the relative max is actually f of 2. Now, let's see. I guess just to be mean or picky, let me see what your guys' is really quick here because since it says find the relative extrema, they might actually want us to calculate this here. So let me see what I put on your guys' worksheet. Okay, so I rechecked it, and we're just gonna ask where is the relative extrema. So let me reword the question. Where are the relative extrema? In that case, let's go ahead and rephrase our answer then, just because this is how you guys will do it on yours. You would say the relative max is at x equals 2. There is no relative min, there is no relative, so that's it. There's just a relative max for this particular question. All right, let's go ahead and move on to number 3. Oh, and by the way, how would you be graded? Well, it's really just a 1-point question. You have to identify it and as a max or a min and give the x value. That's good enough. All right. Let's go ahead and continue. Yeah, there's really not going to be any work to show, so I don't think that would be necessary. Don't worry about showing work on number 2. Really none to show. Let's go ahead and take a look at number 3. All right. Number 3 is asking not for the relative max or min, but for the absolute max and min. And when you're looking for the absolute extrema, you need to do a candidates test. Candidates test is comprised of the endpoints. So our lowest x value is -5 and our highest x value is 8, as well as any critical values that may come up along the way. And so technically, we could check -2 and 2. But really, we don't really need to check -2, just so you know. And the reason why is because it's not a relative extrema anyway. We established that on number 2. So I'll go ahead and skip that one. But I mean, it wouldn't hurt to check it. The only thing it would hurt is maybe take a little more time, but it won't give you a wrong answer. So I'm going to go ahead and leave that out. These are the only candidates we need for that. Okay. Now for the candidates test questions, that there is worth 1 point, correctly identifying your candidates. The next point would be in finding the y values for each of those. Okay. So I lost my word. Back up a little bit. All right, so -5. We're trying to find the max of f, right? So to find f of -5, we would need to do the integral from -2 to -5 of our g function. Now, first of all, you'll notice that the limits are backwards. I have the lower number on the top, so we're going to reverse that. And to do that, we need to put a negative in the front. Okay. Now what I'm going to do is I'm going to go ahead and find the area under the curve from -5 to -2. Now, all of this stuff here is geometry. So we have a square here, which is 4. We have a triangle here. Base times height is 4 times 1. Cut in half is 2. So I'm going to draw a little arrow here to squeeze my 2 in there. Now we have a really weird shape right here. We have this little wedge-looking piece. And we talked about those a while back. The way you get those is by taking a square and subtracting a quarter circle from it. And what remains is that wedge area that we want. So what would the area of the square be? Well, that would be 4, right? Then what would the area of the quarter circle be? Well, that would be pi radius, which in this case is 2, squared divided by 4. Okay, so subtracting those will tell me what the area of that little yellow chunk there is, and that would be 4 minus pi. Okay, so I'll draw a little arrow now. I'm going to erase all this gunk. And I'll draw a little arrow to the yellow region here. Oops. Erase. And we'll say that little chunk is 4 minus pi. Okay. So now if I'm going from -5 to -2, I need this little wedge, I need the 4 and the 2. And so that's going to be negative, because that thing's still out there, right? And we're going to put all those pieces in there. 4 minus pi, 4, and 2. And so what we end up with then is 8 plus 2 is 10 minus pi. And if you distribute the negative, you get pi minus 10, right? Now, that's a negative number. you can think of that as about 3 take away 10. So it's pretty close to about -7. So now we're going to repeat this process for the next few numbers. All right. So now we need to find the area of, let's see, for 2, that's the integral from -2 to 2 of g. So that's this region. Now we calculated that earlier. We actually had to do an integral, and if you missed it, I would encourage you to go back and take a look at number 1. We talked about that, how to find the integral of that, or that area under the curve for that parabola. And if I'm not mistaken, let me see, what did we get for that? What we got for that region was we got -16 over 3 plus 16. Now, if you want to get a common denominator, you can. Kind of already have a good idea of what this would equal. That's good too. 48 take away 16, what would that be? 32. So we end up with 32 over 3, which is just a little bit less than 11. Because 3 goes into 33 11 times, right? So 3 would go into 32 10 times plus something a little bit more. So there's that. All right, let's go ahead and do the last chunk now. The last one is we want to find f of 8. All right, so f of 8, that would be the integral from -2 to 8 of our g function. So what that's going to be including then is that's going to include the parabola, the quarter circle, and this little rectangle right here. That's going all the way from -2 to +8. So we already have the parabola area. We found this area earlier as well. That was 9 pi over 4, but it was negative because it's under the curve. Same thing here. We can do this. That's 3 times 3, so that's 9, and it's negative because it's under the curve. So this area all put together then would be -16 over 3 plus 16 minus 9 pi over 4 minus 9. And just so you guys know, yours is going to come out to work out a heck of a lot nicer. I made sure you guys didn't get all these weird funky fractions on most of it. But it doesn't really matter. I'm just showing you guys how to get this stuff. So let's go ahead and do this. I'm just going to circle this, and I'm going to put my answer there. And I'm going to estimate what that, well, I'm just going to use my calculator, honestly, because, like I said, I'm not giving you guys something to do like this. It's honestly just too much to stress over at the moment. So give me a minute, and I'm going to punch it on my calculator so I can quickly get a nice answer. And I'm getting about -5.402. Okay, so we said this one here was about -7. This one here is just a little bit less than 11. And this was -5. So let's answer our question now. We can actually answer the question. And this is where your last point will come in. So this is a 3-point question. You get 1 point for your candidates, 1 point for your outputs, and don't worry, yours won't be as ugly as mine. The last point will be, did you identify the absolute max and min? So the absolute max in this case, now notice I'm not going to change the question this time to where is the absolute max. I'm just going to leave it as what is the absolute max. And that means it's a y value. So what's the biggest y value that we have, or the biggest f of x value? It's 32 thirds. And my absolute min, that means the smallest y value, that was this one. So pi minus 10. Okay, so candidates test for number 3, 3 points. Okay, so for number 4, I have broken number 4 up into 2 parts, an A and a B. You guys only have 1 part on yours, but I'm just going to go over some different scenarios to give you guys a more well-rounded answer. So find the average rate of change of g on the interval from 0 to 5. So that's my first task. And then, does the mean value theorem guarantee that there exists some value c on the interval 0 to 5 such that g prime of c equals the average rate of change? Justify your answer. So there's two things that we have to do here. I'm going to try to keep that second part simple for now, and then I'll explain it in a minute. But the two things we need to do is we need to find the average rate of change, and then we need to know, does the mean value theorem apply to this function on that interval? Okay, so let's go ahead and start with the average rate of change. The average rate of change is basically the slope of the secant line between these 2 points, 0 and 5. So to find the slope of the secant line from 0 to 5, we just need to find the y2 minus y1 over x2 minus x1, right? So that's going to be g of 5 minus g of 0 over 5 minus 0. G of 5 is negative 3, minus g of 0 is 4, and 5 minus 0 is 5. So that would be negative 7/5. Okay. Now, the mean value theorem, what is that? The mean value theorem, just in case you guys forgot, it's a theorem that basically says that your function has some point along the curve where the slope, the instantaneous rate of change, is equal to the average rate of change. In other words, the lines are parallel. Okay. However, the mean value theorem has some limitations to it. The function has to be continuous and differentiable. Well, g of x is continuous on this interval. It is. However, it's not differentiable. The reason why is way back in the beginning of our instructions, we talked about this. And I told you guys that that meant right here, even though it's not quite visible to the eye, there is a little bit of a cusp. And at a cusp, there is no derivative. So this function is not differentiable on the interval from 0 to 5 because somewhere in there there's a cusp, and therefore we can't do it. So let's go ahead and talk about how you should be graded on this. So first of all, this would be 1 point here. Just getting from here to here and showing your work as you go. Okay, that's 1 point. The next point would be saying, no, the MVT does not apply on the interval 0, 5 because g prime of, well, you just to keep it simple, we could say it's not differentiable on that interval. So the mean value theorem does not apply on the interval from 0 to 5 because I shouldn't say it, that wasn't good. We don't say it in this class. We have to define it. Sorry about that. Because g of x is not differentiable for all x on that interval. Okay? And that would be a second point, giving a correct answer with an explanation. All right? Now, let's take a look at part B. And for part B, it says find the average rate of change again, but this time on a different interval, -1 to 2. And this time, does the MVT guarantee that there is some value c on the interval, blah, blah, blah. Okay, so let's go ahead and start here. So g of 2 minus g of -1 over 2 minus a -1. All right, so g of 2, am I doing this right? 2 to -1, yeah. All right, so g of 2 is 0, minus g of -1 is 3, over, that makes 3, simplifies to -1. So there's your +1, that's your average rate of change. Now, look at this interval. We have a nice smooth curve, a parabola in fact. Does the mean value theorem guarantee that there would be a slope somewhere on this interval that would equal this average rate of change? And the answer is yes this time, because we have a continuous and differentiable function on that interval. And therefore, yes, somewhere along the way, we can be sure that there is a line that's parallel to our average. So on this one, we would, for our second point, we would say yes, MVT guarantees there is a C on the interval -1, 2, such that G prime of C equals my average rate of change, since G of T is continuous and differentiable on that interval of -1 to 2. So there you have it. Okay, moving on to number 5. Okay, part A, once again, it says 1, but it's really number 5. Let me fix that. Once again, I'm going to do an A and a B just to give you a well-rounded answer. Where is F concave up? All right, well, F is concave up when F double prime, which before we established that F double prime is G prime, is greater than 0. Or you could just say positive. So the function F is concave up when F double prime, which we established earlier is the same thing as G prime, is greater than 0. So now we need to state this because the question is asking about F. However, we need to state this as well because that's the fact that we're going to use to answer the question. And so now we're going to state, where is G prime of x greater than 0? G prime of x is greater than 0 on the following intervals. Well, remember, that's the slope. So when is this graph over here, when does this graph of G have a positive slope? Well, it has one here, it has a positive slope here, and that's it. So we would say it's concave up on -5 to -3. And it's concave up on the interval -2 to 4. And they don't really care whether you use brackets or not. Okay. Now, if you want to do the opposite, part B is asking, when is this graph concave down? I'm going to make a couple of changes. F is concave down when F double prime, which is G prime, is less than 0. And G prime is less than 0 on the following intervals. Anywhere where the slope, which is G prime of x, anywhere where the slope is negative. Well, that would be here, and here, here. We don't want to include this last straight line because that's not a negative slope. That's a 0 slope. That's not negative. So my intervals would be from -3 to -2, as well as 0 to 2, as well as 2 to 5. Okay? All right. Now the reason why I decided, instead of just saying it was, it's a technicality, but instead of just saying that, instead of just putting these together as going from 0 to 5, I broke it up. And the reason for that is because there's a cusp here, which means the derivative doesn't exist, which means that f double prime doesn't exist, and therefore that's not a good argument for whether or not f concave down at that point or not. So I'm just going to split it up, and technically we might want to use some parentheses there. But like I said, that's a technicality. Let's go ahead and, and how would you be graded on this one? Well, actually on your guys' question, once again, it does two things at once. It asks you about concavity, but it also asks you about where is F increasing and decreasing, which is a different question. Okay, so now F is increasing. When F prime, which is equal to G, which we established earlier, is positive. F is increasing when F prime, which is the same thing as G, is positive. In other words, when the slope of F is positive, right? Now, the slope of F is just this graph over here, G. So anywhere where G is positive, well, G is positive from here to here and from here to here, because it's all above the y-axis. So we would say that that happens then on the intervals of -5 to -2, and then from -2 to 2. And technically would use parentheses here and a bracket on the endpoint, because over here the -5 is a positive, but these 2 points are 0. They're not positive or negative. But once again, that's a technicality. I don't think they really care about parentheses, and I wouldn't be grading you on it. And of course, to change the question a little bit, where is F decreasing? F is decreasing when F prime, which is G, is negative. And where does that happen? Well, that's this entire interval over here. So that would be a nice simple answer of 2 to 8. And actually the 2 is on the line, so we would give that a parenthesis. Okay. Now your guys' question asks you to do 2 things at once. So for instance, suppose I asked you guys, where is F increasing and concave up? Where is F well, actually, let me change it up a little bit. So if I asked you, where is F increasing and concave up? Well, that means we're looking for a place where F prime is greater than 0 and F double prime is greater than 0. In other words, where G is greater than 0 and where G prime is greater than 0. Or yet still, in other words, where G is above x-axis and where G is sloped up. So where is G both above the x-axis and sloping upwards? Where is G both above the x-axis and sloping upwards? Well, that would be here and here. Okay. So that being said, I'll go ahead and move on to number 6. All right. Number 6 is asking us where is a point of inflection and give a reason for your answer. All right. Let's see. Point of inflection. A point of inflection, in case you guys forgot, that's a place where the concavity changes from positive to negative or negative to positive. So in other words, F double prime is changing from positive to negative or from negative to positive. Now, as we already established before, F double prime is G prime, which is the slope of G. So in other words, where at on this graph over here is the slope of G going from positive to negative? Here's a spot. To the left, the slope is positive, but to the right, it's negative. Here's another spot. To the left, the slope is negative, but to the right, it's positive. Here's another spot. To the left, the slope is positive, but to the right, the slope is negative. I don't see any other points of inflection. Okay, so here's how we would answer that particular question. We would say F has a point of inflection. You don't want to say POI on your FRQs. That's not official math language. That's just Mr. Bailey being lazy. F has a point of inflection at x equals -3, 0, and -2. Since F double prime, which is equal to G prime, changes signs at that point. Okay. There you have it. Let's continue here. Last question. Part A, that is. All right. Let h prime of x equal 2g on the interval from -3 to 2. If h of -3 is 1, find h of 2. Now I want you guys to notice something. We're going from a derivative, a fact about a derivative, to a fact about an original. How do you go from a derivative to an original? The answer is integration. So the integral of h prime of x gives us h of x, right? However, we're going to do a little change here. We're on an interval. So now when you do an integral on an interval, those are your limits. So we're going from -3 to -2. And when you have a definite integral, you plug in the upper limit and you subtract that from the lower limit on the other side. Okay? Now let's go ahead and focus on this side really quick. On this side, we know that h prime is the same thing as 2g. So I'm going to rewrite that. I'm going to put 2g in here instead of h prime. Why can I do that? Because they're exactly the same. Now instead of putting the 2 right in front of the g, I'm going to put it out here, because when it comes to integrals, you're allowed to pull them out of the integral. I'm sorry, when it comes to constants, you're allowed to pull them out, but not variables, only constant numbers. Okay, on this side, I think I'll just go ahead and leave it for now. We'll come back to this side in a minute. All right, so what we need to do then is we need to find the integral of g from -3 to -2. In other words, what's the area under the curve from -3 to -2? Here to here, and that's the triangle. And we already calculated that a little bit earlier. The area of that triangle was 2, right? So we have the 2 on the outside, and the area under the curve is 2. Okay. So now we have 4. 2 times 2 is 4. Equals, now, h of -3, I know what that is. They told me. H of -3 is 1. So I'm going to rewrite h of -3 as 1. And since I want to find h of -2, all I have to do is minus the 1 on both sides, and I've got my answer. Okay, so that's the end of part A for your FRQs. Let's move on to part B. So for part B, we've got a table that gives us the values of f, f prime, and f double prime. It tells us where, what maybe their values are at specific points, but also at intervals between those points. They also tell us that the function f is continuous on this interval. Okay, so let's go ahead and take a look at number 1. Can we use the mean value theorem to show that there's a value c on the interval 0 to 2 for which f prime of c is equal to 1? So, in other words, can we do this? Can we say that f of 2 minus f of 0 over 2 minus 0 is equal to -1, which is going to be some value f prime of c. Well, if you were to try to calculate this, which you could, f of 2 is 0, f of 0 is 2, you might actually end up with -1. Okay, but here's the thing. You only are allowed to do this if the function's continuous and differentiable on the interval. Well, we know it's continuous, they told us, but is it differentiable? To know that, we would need to look at this derivative column here. Look between the numbers 0 and 2. Is the derivative undefined anywhere on the interval from 0 to 2? Well, it's undefined here, but that's actually okay. When it comes to the mean value theorem, the endpoints don't have to have a derivative, just the things in the middle. So do I have an undefined derivative anywhere in here? No. The derivative exists everywhere on the interval. So we're good. We can actually go ahead and go forward and see if it works. So let's calculate it now. So I don't want to put equals -1 yet, because I'm not sure about that. But let's see. What is f of 2? F of 2 is 0. And what is f of 0? F of 0 is 2. And 2 minus 0 is 2. And if we go ahead and simplify this, we do get -1. So since the math works out, we're going to say yes. Now, here, how would you explain your reasoning? Because once again, we're looking at probably a 2-point question. One for the correct answer and one for your explanation. So your explanation would have to include all the work I just showed from here to here. Okay, and then you would also have to say yes, since f is continuous on the closed interval 0 to 2, and it's differentiable on the open interval 0 to 2. Notice it's open. Remember, I said the endpoints don't matter for differentiability. There is a C for which f prime of C equals -1. But you're only going to get credit for stating this fact if you've already shown the math that doing these numbers actually gives you -1. Okay, so this would be your 2 points, but remember, you have to show your work where the -1 came from. Right? And this even though it's 2 points, this is really kind of an all or nothing kind of situation. You technically you're getting a point for the correct answer, but you can't get a point for this unless you say this statement. Okay. Now, what is possible is that you say the statement in a decent way, but you have the wrong conclusion. That would be worth 1 point. But let's go ahead and take a look at another one. All right, so for number 9, can we use the mean value theorem to show that there's a value c on the interval from -1 to 1 for which the derivative equals -3/2? Okay, so from -1 to 1. Well, we could do this math once again. Let's work it out really quick just for the heck of it. Let's see, -3, 0, 2, and we do in fact get -3/2. But even though we do get -3/2 by finding the average rate of change, we can't be sure that there is some value c that will give you that instantaneous rate of change if you plug it into f. We can only know that if the function is continuous, which it is, and if it's differentiable on the interval. Let's take a look and see if it's differentiable on the interval from -1 to 1. Well, remember, we don't care about the endpoints. For differentiability, we don't. Continuity, we do. Differentiability, we don't. You need the continuity because otherwise you can't plug them into the function. But the derivative does not have to exist at the endpoints. Anyway, back to the problem. But as you guys can see, we do have the function as no derivative on the interval there. There's a place on this function where the derivative does not exist, and therefore we can't be sure of this. We can't be sure because what if that's the one spot where the derivative would have equaled -3/2, but that's where it's undefined? And so we can't be sure. So here's how you would answer this question. You don't actually need to show the math at all on this. You can just say no, since f is not differentiable on the interval -1 to 1. It has a discontinuity in its derivative. Okay, so that's number 9. So number 10 is another IVT question. This time we want to know, is there a place on the interval from -2 to 1 where the function equals -1? So as we're going from -2 to 1, we know that the function is continuous, and that's all that's really required for the intermediate value theorem, so we're good there. And we are going from a y value of 4 to a y value of 3, and the y value we're trying to work to is included in that interval. So the IVT does apply. So the way we would say that is we could say since f is continuous on the interval -2 to 1 and goes from 4 to -3, there must be a c such that f of c equals -1. Okay, so that's number 10. Let's move on to number 11. So for number 11, we're looking for the absolute extrema. So we're looking for the greatest and smallest y values. It'll be a little bit easier than part A's was, I believe. So how we do this is we do our candidates, right? We do our endpoints, which the lowest x value is -2 and the highest one is +2. And then we include any places on that interval where the derivative is either 0 or undefined. Those are our critical values. So it looks like every possible point is included there that we're given anyway. So -1, 0, and 1 are all critical values. And so what we need to do now is we just need to find out, well, what is f of x at each of those points? But the good news is it's pretty easy. They just give it to you. So at -2, f of x is 4, next one is 0, 2, -3, and then 0. And so we can see that this one would be our max, and this one would be our min. So let's go ahead and check out number 12. This one says where are the relative extrema, not what are the relative extrema. So in this case, they want the x values. Now, relative extrema can happen at critical values. So first of all, we want to identify our critical values, and those are anywhere where the function derivative is 0 or undefined. And we found those last time. The derivative is going to be 0 or undefined here, here, and here. We're not going to include endpoints. We don't look for relative extrema at endpoints. We only do in between the endpoints for relative extrema. It's the absolute extrema that we include the endpoints for. So we really just need to look at the following x values, -1, 0, and 0. Now, just because they're critical values doesn't mean that they're relative extrema. They are relative extrema if they change, if the derivative changes signs at that point. So let's take a look here. As you can see for the first one, undefined, the slope goes from negative to positive. When that happens, it's a relative minimum. So that would be a relative min. For the 0 one, or yeah, for the next one, it goes from positive to negative. So that's another relative extrema. When you go from positive slope to a negative, that gives you a relative max. And then for the last one there, we're 0. We're going from negative to positive. So that's another relative min. Now, how you need to write your answer for this would be, I don't think that you're not going to get points for this picture. So, and they are going to ask you to explain your reasoning so that the picture is not an explanation, just so you know. So let me show you how you would word your answer here real quick. So negative 1 and 0 are the relative mins, right? So I'd say, let me change my color, since f prime changes from negative to positive at x equals negative 1 and x equals 0, those are where f has a relative min. It's hard to write on my screen. Sorry for the nasty handwriting. And then we can just rephrase it for the other part. We can say since f prime goes from positive to negative at x equals 0, f has a relative max at that point. Okay, so that's the end of 12. Let's move on to 13. All right, number 13. I broke it up into 2 parts. First one is, where is f concave down and concave up? F is concave down and up anytime. Well, let's go ahead and put this. F is concave down when f double prime is less than 0, or negative is another way of saying that. And so we have from negative 2 to 1, negative 1 I mean. Once again, I don't think they really care about brackets and parentheses, but I'm using a bracket because negative 2, it is concave down at negative 2, but it is not concave down at negative 1, so I'm not going to include the negative 1 in the interval. F is also going to be concave down here, so we can put negative 1 to 0, and that's it. There's no other places where f double prime is negative. Okay? And then we can restate the thing with concave up. The only difference is now is that f double prime is going to be greater than 0, positive. Right? And so that's going to be happening from the whole interval here, all the way from 0 up to 2. And we're not going to include 0 in the interval because there the second derivative is undefined, but we are going to include 2 in the interval because there the second derivative is positive. So I would say from 0 to 2 would be good enough. Okay. The next question is asking us, where is f increasing and decreasing? So a function is increasing or decreasing based on the sign value of the derivative. So f increases when f prime is greater than 0. So anywhere where the second or the first derivative is greater than 0, f would be increasing. So that would be here and here. So my 2 intervals that I would give for that would be from -1 to 0, as well as, let's see, 1 to 2. Okay, and then where would it be decreasing? That would be where the derivative is less than 0. And so we have that here. Oop, wrong. We have it here, and we have it here. And so the intervals there would be from -2 to -1, as well as -1 to 0. Now in your guys' portion of this exam, it asks you where is the function like concave up and decreasing. So like, or something like that, right? So if I were to randomly pick, this interval here from -1 to 0, well, on this interval, since the first derivative is positive, the function's increasing on that interval. But since the second derivative is negative, it's concave down. So concave down increasing would look something like that. The function is increasing, but it's bending in a downward direction. Okay, so for your guys' portion on the FRQ, you'll have to look at the f prime and f double prime simultaneously to be able to answer that question. All right, moving on to number 14 is asking us where, once again that's the next value, where does the graph of f have a point of inflection? So we would say that f has a point of inflection when f double prime changes signs. So in other words, when it goes from positive to negative or negative to positive. So we have negative, negative, negative. Whoop, there we go. We just switched there. At this point, at x equals 0, the second derivative changed from negative to positive. So we would say that happens at x equals 0. Keep going, positive, positive, positive. There's no other points of inflection there. It only switches once. So there you have it. Number 15. All right, so for number 15, you're asked to actually turn this whole thing into a picture. My advice is to start with the points first. Plot all of the points that they give you first on an x and y axis. So we have the point -2, 4 first. So there's that point. Then we have -1, 0, 0, 2. Use a different color here. I can't see so well. And then we have 1, -3. And then we have 2, 0. All right, there's our points. Now, after you do that, what I would say you want to do is you want to look at the slope and the concavity in between the points simultaneously. So like in between -2 and -1, I would say look at the slope and the concavity simultaneously. So this means that your function's going in a downward direction because it's decreasing, but this means it's concave down. So concave down in a downward direction would look something like that. So as I'm connecting this dot to this dot, I'm going to connect it with a downward going concave down line, just like that. Bending down and it's going down. For the next interval between points from -1 to 0, we can see that my slope is positive, but it's concave down. So we're going up and it's concave down. So that would look like this. So as I go from this point to this point, we're going to have a sharp turn all of a sudden here, and it's going to be bending downwards like that. The next interval between 0 and 1, we have a negative slope but a positive concavity. So that means our graph is going in a downward direction, but it's bending up. So that would look like this. So this is going to be kind of tricky for me and how far I've spaced these points apart, but it's going to connect these in that fashion. So let me do my best to make a curved line curving too much. There we go. So it's going down and it's concave. Last one, positive and positive. So that means we're going up and we're concave up. So that's going to look like this, going up and concave up. Notice also, just for the heck of it here, that at x equals 1, the slope is 0, so the slope's not undefined, so this would be a smooth curve here. Whereas at this point and at this point, at x equals -1 and 0, we would have a cusp because the derivative's not defined. So here we would have some sharp turns, but at this point we would have a nice smooth turn because the derivative actually exists at that point. Okay, so there you have it. That's the end of your FRQ.